Alrighty, folks, angles and polygons now are going to be kind of related to what we've been doing all along here, and we're going to step outside our realm of just angles and triangles. We're going to take polygons of even more sides and angles and all that stuff. We're going to look for some patterns when it comes to their angles, okay? So let's see what we've got. Angles and polygons. Sum of the interior angles in polygons is important, and a formula for the sum of the interior angles. And then we're going to look at angles in regular polygons and find out why the other ones are kind of irregular, but we'll see what's going on. Alrighty. Okay. Alright, so we're going to look at the sum of the interior angles in polygons, but I'm going to qualify this a little bit. And usually we just assume it, but without saying it, but I'm going to make sure that we say convex polygons. Okay? So we're not looking at a polygon that has a shape like this. Okay, that would be a concave polygon because it's got this sort of cave in it, right? So we're just looking at convex polygons for now. So make sure you're aware of that, okay? So it says we're going to look at the sum of the interior angles. So let's take a look. We already know for a triangle that the sum of our interior angles is 180 degrees. Any triangle at all, that always works. Okay, so that's a pretty good one. And then we're going to take sort of a little journey here, and we're going to step through going from our three-sided figure, four-sided, five-sided, etc., and go all the way up to the octagon and see what we can figure out. So if I'm looking at a quadrilateral, and a quadrilateral is any four-sided convex polygon. So it could be like a square, a rectangle, a parallelogram, a rhombus, a kite, anything that's got four sides and it's convex. So what you'll notice is that you can sort of take your diagram and you can slice it in half just by going from one opposite corner to another and create a diagonal. And what you'll quickly realize is that creates two triangles inside. And the interior angles of all those triangles, each triangle has to add up to 180 degrees. So we have 180 there and we have 180 there. And if that's the case, all we have to do to find the total of all the interior angles is to say we have 2 times 180 because I have two triangles there. So it's 360 degrees. Okay, so for a convex quadrilateral, we've got 360 degrees for the sum of our interior angles. What about a pentagon? So we'll go to 5 sides now. Well, we're going to use the same sort of theory. We're going to split this into, by connecting certain diagonals. Let's just see the points we're using here first. We're going to split this into 3 triangles. So we have one triangle for a 3-sided figure. For a 4-sided figure, we can create that with 2 triangles. Any pentagon that's convex can be created, as you can see, from 3 triangles. So adding all those angles up, we have 3 times 180 degrees for our pentagon. So 3 times the number of angles in a triangle, is 3 times 180 here, and that gives us 540 degrees. Okay, so by now, since we're so great at inductive reasoning, we should be starting to recognize a pattern. If I go to a hexagon, well, let's see. How many triangles do we break it into? 1, 2, 3, 4 by dividing it up. So basically for a hexagon then, I just take 4 multiplied by 180 degrees, and I get 720 degrees inside. For a heptagon, sometimes called a septagon, but it's a heptagon correctly, I believe, which is a quadrilateral with 7 sides. Let's see, we've got 1, 2, 3, 4, 5 triangles. So our sum of our interior angles will be 5 times 180, which is 900 degrees. And then for an octagon with 8 sides, let's see, we've got 1, 2, 3, 4, 5, 6 triangles, and that gives us 6 times 180, or 1080 degrees. Okay, so we can see that there's definitely a pattern. It's just about the number of triangles that we get. So let's see if we can make this pattern a little clearer. So for a triangle, we had 3 sides, and it was just 180 degrees. For a quadrilateral, we had 4 sides, and it was 2 times 180. For a pentagon, 5 sides, 3 times 180, etc., all the way down here. So what we're really doing is we're just adding an extra 180 degrees every time. And notice the correspondence between the number of sides that you have there. So if we look here, we've got 8 sides, and we multiply 180 by 6. When we had, say, 5 sides, we multiplied 180 by 3. So we're always multiplying 180 degrees times 2 taken away from the number of sides that we had. So it's n for the number of sides, so we multiply by n minus 2 times 180 to get the sum of all of our interior angles. And we write that as a formula. We say that the sum of the interior angles for a convex polygon, sum for n angles, is 180 degrees multiplied by n minus 2. So if you have 8 angles and sides, then you're going to take n minus 2, so the number of sides minus 2 times 180. Okay? Not all that bad. Now, what happens if we have a regular polygon? So by a regular polygon, basically, if I had that quadrilateral, but it would have to be a perfect square. That's a regular polygon, or a rhombus. A regular polygon, no, it would have to be a perfect square. Sorry, all the angles have to be the same. A regular polygon has all of the sides and angles are congruent. Well, if all the sides and the angles are the same, then all I'd have to do would be to take the sum of all my angles, the total, and divide by how many angles I have, and they'd all have to equal that much. So, since all angles are congruent, then each angle in the polygon would have to be the sum of the angles divided by n, where we had n angles. So it'd be 180 degrees times n minus 2, all divided by n. And those are the two formulae that we use when we're dealing with convex polygons. So one for regular and one for irregular. So remember, when we're dealing with the sum of the interior angles for a convex polygon, or any n-gon, it's 180 times n minus 2, and then if it's a regular polygon, each angle would just be that divided by n. Okay, so we'll do some problems with those in the next section. Thanks.